Hello, welcome back. Today we'll look at multiple angle formulas, and so we're going to be able to find even more solutions uh, from the 5-4 section where we covered sum and difference. So considering the first example, we want to substitute cosine of 2x with one of the double angle formulas. And you may notice that there are several to choose from. So we're going to just choose the one that has strictly cosine and substitute cosine of 2x with 2 times cosine of squared of x minus 1 plus cosine of x. Now I could rearrange these and we can easily factor this so that we'll have 2 times cosine of x minus 1 cosine of x plus 1. And then when we solve for this, we can set each factor equal to 0 and then solve for x. So we know that cosine of x will equal 1/2 and cosine of x will equal -1. Well, just considering a unit circle, well, cosine of x equals 1/2 at pi over 3 and 5 pi over 3. But this question was looking for all the solutions. So just make sure you include plus 2 pi n to include the periodic changes. 5 pi over 3 was our second solution, plus 2 pi n. And then cosine of x is going to equal -1 at pi. So pi plus 2 pi n. So we'll have 3 general solutions. Now let's practice finding these double angles. We're given that u is in the second quadrant, and we know that the sine is positive, and the cosine, or the x-coordinate, will be negative. So if we're asked to find sine of 2u, well, that's just going to be 2 times the sine of u times the cosine of u. So we know that the sine of u was at 3/5, and the cosine was -4/5. So we can simplify that to be -24 over 25. To find the cosine, you have a couple choices. You can use any of those 3 formulas. So I'll just use cosine squared minus sine squared. We know that the cosine again was -4/5. The sine was 3/5. We square those and find the difference. We'll have 7 over 25. Now for the tangent of 2u, that's just going to be the 2 times tangent of u over 1 minus tangent squared. Again, we know that this is in the second quadrant, so tangent will be negative. So it's 2 times -3 over 4 over 1 minus -3/4 squared. And we can simplify that to equal, that's going to be -3/2. I'll write this over here, -3/2 over 7 over 16. So we'll get -3/2. We could multiply the reciprocal. It's a 7. So we'll get -24 over 7. So practicing finding those formulas, those double angles, sine of 2u, cosine of 2u, and then tangent of 2u. And it's good to note that considering these values, if u was in the second quadrant and we doubled it, 2u would be in the fourth quadrant. So sine is negative, cosine is positive, and tangent is negative. I've covered the double identities, so now let's actually derive the triple angle formula and write that in terms of cosine of x. And we can rewrite cosine of 3x as cosine of 2x plus x. And now using the sum identity, so this can become cosine of 2x, cosine of x, minus sine of 2x, sine of x. And now we can substitute in those double angles. So cosine of 2x is 1 minus 2 times sine squared and cosine and sine of 2x is 2 times the sine of x cosine of x, or we still have that sine of x. So I'm going to just simplify this a little bit. So we have cosine of x minus 2 times sine squared times cosine of x minus 2 times sine squared, and that's going to be a cosine of x here. So we do have like terms, so we can rewrite this as cosine of x minus 4 times sine squared cosine of x. And remember, let me just make sure I write my x. We can substitute the sine squared because we want this in terms of all cosines. So what I'm going to do is use the Pythagorean identity. So this is 1 minus cosine squared of x. And now let's just rewrite this a little bit. So we have cosine of x minus 4 cosine of x minus, that'll be plus 4 cosine cubed of x. All right, so we actually have another set of log terms here. So I'm going to rewrite this as 4 cosine cubed minus 3 times the cosine of x. So now we have only cosines and no double and triple angles anymore. All right, so we're going to look at the power reducing formulas. So here we have cosine squared, and it looks very similar to the double angle formulas. So we're going to rewrite g of x in terms of a double angle. So when we have g of x, we can actually substitute in sine squared. So this is 3 minus 6 times 1 minus cosine of 2x over 2. Well, there's some easy reducing here. That will just be equal to 3. So we'll have 3 minus 3 plus cosine 3 times cosine of 2x. So that just equals 3 times the cosine of 2x, and that's in terms of a double angle. All right, now we're going to rewrite tangent of 4, or tangent x to the 4th as a quotient of powers of cosines. So we can first separate tangent raised to the 4th as tangent squared times tangent squared, or tangent squared quantity squared. So essentially it's going to be 1 minus cosine of 2x over 1 plus cosine of 2x quantity squared. And we can rewrite this as 1 minus 2 times the cosine of 2x plus cosine squared of 2x. And then on the bottom it'll be 1 plus 2 times the cosine of 2x plus cosine squared of 2x. Now here we have a double angle, so I can rewrite this double angle, right, this right here. So this will become cosine squared of 2x, so we're going to have 1, let's rewrite this here. So we have 1 minus 2 cosine of 2x. I'll leave that in double angles here. But the squared becomes 1 plus cosine of 4x. Remember, we're taking that degree, that measure, and doubling it over 2. So we're making a complex fraction here. And we have 1 plus 2 cosine of 2x. And that's 1 plus cosine of 4x over 2. All right, when we find a common denominator, we're going to multiply everything by 2 here. So essentially it's going to become, and I'm going to write it right here so I have some room, 2 minus 4 cosine of 2u, or 2x, plus 1 plus cosine of 4x. And then on the bottom we'll have 2 plus 4 cosine 2x plus 1 plus cosine of 4x. So let me just rewrite this and combine like terms. We have that 2 plus 3. So it'll be cosine of 4x minus 4 times the cosine of 2x plus 3 over cosine of 4x plus 4 cosine of 2x plus 3. So we rewrote tangent raised to the fourth in terms of cosine with multiple angles. Now let's consider half angles. So when we look at half angles, we're actually going to be taking the square root. Noticing we're having that squared, now it's going to be the square root. Whenever we have a plus or minus, we're actually going to just make sure that we check the quadrant in which u over 2 lies to determine if sine or cosine is positive or negative. All right, so for this example, we're going to find the exact value of cosine of 105. And before we did this, you weren't able to do that in exact form. So we're going to use cosine 105, but we have to think of its double angle. So if we doubled 105, we would get 210. So 210 divided by 2 would give us that 105, and we can use the half angle formula. So just remember cosine of 105. Well, 105 is in the second quadrant, right? So that's going to be a negative. So we're going to have negative times the square root of 1 plus cosine of 210, and it's in degrees. I'm just writing 210 over 2. All right, well, we can simplify that. So the cosine of 210 is going to be 1, let's say minus root 3 over 2. We can write that over 2. All right, now we're going to have to simplify this a little bit more so we can find a common denominator. So we'll have negative root 2 minus, we'll have 2 minus root 3 over 4. And this is under the same radical here. And I can simplify this a little bit further. So we have negative, and it'll be a radical with a radical. So 2 minus the square root of 3 over 2. And that's as far as we can go. And that is actually the exact form for the cosine of 105. For the next problem, we're going to use half angle formulas to find the solutions. So remember, sine squared of x over 2. Well, remember the sine was always, the half angle was just the square root. So if we square it, it'll just be that radical squared. So it'll just be cosine of squared of x equals 1 minus cosine of x over 2. So we can multiply everything by 2 here. And then set this equation equal to 0. And we'll have 2 cosine of x. In fact, this factor before, cosine of x plus 1. So we know that cosine of x will equal 1/2. Cosine of x will equal negative 1/2, or negative 1. And for those solutions, we know that cosine will equal 1/2 at pi over 3 and 5 pi over 3. And the cosine will equal negative 1 at pi. So we have 3 solutions between 0 and 2 pi. For this last example, we're actually going to look at place kickers. So here we have Justin Tucker from the Baltimore Ravens, probably one of the best place kickers in the league. And we want to find the angle at which a player needs to kick the ball so that it travels 188 feet. So r is that horizontal distance. So I'm going to set this equation equal to r. We're given that the initial velocity is 78 feet per second. So I'll substitute that in. And when I look at the equation, there's definitely some double angle in there. So we know that 2 times sine of theta cosine theta is sine of 2 theta. So what you can do is rewrite this, so we have 1 over 32, and this will be 2 times the sine of theta cosine of theta. So we can substitute this, and I'm just going to write these together here. That's going to be sine of 2 theta. So we can divide everything by 78 squared, multiply by 32, so we'll get sine of 2 theta equal to 1,504 over 1,521. And so from here, we just have to take the arc sine, or the inverse sine. And then, just to find theta, we just need to divide this by 2. Let's put 1/2 in front. So this would be calculator ready form. And if you wanted to find that angle that the place kicker should kick the football, that would be approximately 40 degrees, or 40.71 degrees. I hope this lesson was helpful, and I'll see you all in class.